All right, so instead of creating a triangulation of forces each time, we can do what we call is resolve the forces. And so resolving the forces typically is we try to work out what component of the force is acting in one direction, which one's acting in the opposite direction. And often we often work with parallel and perpendicular to the direction of motion. Okay, so if there's no motion, horizontal and vertical, because gravity is acting vertically down, we want to typically work out what forces are acting vertically down, and what forces are acting perpendicular to that, which would make them horizontal. That's for our stationary particle or our particle that's not on any inclined plane. So let's have a look at this example. So we've got a particle of mass 8 kilograms is suspended by a 10 centimeter string attached to 2 points in the same horizontal plane 6 centimeters apart. All right. If it's in equilibrium, find the tension in the string. So we can assume from this that our particle slides along the string equally. So in reality, if I've got this 6 centimeter string here, I've got undo that. I've got two 5 centimeter lengths, okay, for my triangle, and a 6 centimeter base. So, and if I break that down, if I just grab half of that triangle, I've got a 5 centimeter length, a 3 centimeter base. From Pythagoras' theorem, it makes it a 3, 4, 5 triangle. Okay. Now, because these two lengths are both 5, it's in fact not only a 3, 4, 5 triangle, but it's an isosceles triangle. Yeah, the big one's isosceles, so they're making 45-degree angles at the roof. So from that information, okay, we know the angles. So what we do in terms of resolving the forces, we tend to identify an I and a j direction, perpendicular to and parallel to gravity if our particle is on a flat surface, if you like, or if it's hanging freely, perpendicular and parallel to the plane if it's on an inclined surface. So if I consider all the forces acting horizontally, so the only force, I've got this tension force T2 acting up to the right, which means I could split this up into a horizontal force, I've just made it pink, and a vertical force there in yellow. All right, so I've got this pink horizontal force here, T2 cos 45, acting to the right, and I've got an equal and opposite one acting to the left because my particle is stationary, T1 cos 45. Cos 45 because it's the adjacent side, and really, if I just draw that triangle out here, that's T1, that's 45 degrees, so that's the adjacent side, and that's the opposite side. Yeah, so in the I direction, I've got two forces acting, T1 cos 45 to the left, T2 cos 45 to the right. And in fact, they are equal because my particle is not being pulled one way or the other. Given the angles are the same, clearly from there, we're going to know that T1 is equal to T2, which is what we kind of expected since our string was free moving, or our weight was free moving, and our string lengths were the same size. Let's consider the J direction, vertically up and down. What forces have I got acting up? Well, initially on the left here, I've got T1 sine 45 acting vertically up. On the right-hand side, I've got T2 sine 45 acting vertically up. And I've obviously got my green weight, the 8 kilogram weight, acting vertically down. And again, my particle is stationary. So those weight forces acting up must be same as the tension forces acting up must be equal to the weight force acting down. So there's my two equations, if you like. Now, from the I component, as I said a bit earlier, I know that T1 is equal to T2. So the J direction equation, I've got two unknowns, T1 and T2, but they happen to be equal to each other in this case. So if I just substitute T1 in for T2, so sine of 45 is root 2 on 2. So T1 root 2 on 2 plus T1 root 2 on 2 is 2 root 2 on 2. So I get 2 root 2's on 2. So I get root 2 T1 is equal to the 8 kilogram weight, divide by root 2, and then rationalise my expression. So I get T1 is in fact 4 root 2 kilogram weight, which must be the same as T2. Okay, so the process is set up your force diagram, and then you break down the components of your forces into equal directions. All right, so if they're acting vertically and horizontally, we break them up into the respective components, and then use the two equations with two unknowns to typically find our tension forces, because the tensions aren't always the same, okay, as we'll have a look at now. So again, same sort of thing. We've got an 8 kilogram weight force acting vertically down. Two strings are attached to 2 points, so two different strings. The two strings make an angle of 30 degrees and 45 degrees. Okay, to the horizontal, find the tension in each string. All right, so again, if that angle in here is 45 degrees, that's the alternate angle in here, that's 45. If the one on the right-hand side is 30, that's my alternate angle there, which is also 30. All right, so resolving my forces, this adjacent side here is T2 cos 30. This opposite side here is T2 sine 30. If I go to the left-hand side, the adjacent side, I've written that the wrong way around, haven't I? The adjacent side, let's just tidy that up. T1 cos 45, the opposite side, T1 sine 45. I might get away with that because sine 45 and cos 45 are equal. So if I keep moving now into my I direction and J direction, so I probably should make it a bit clearer. I direction horizontal, J direction vertical. My I direction, T2 cos 30 acting to the right has to equal T1 cos 45 acting to the left. And in the J component, T2 sine 45 acting up, plus the T1 sine 45 also acting up, has to equal the 8 kilogram weight acting down. So if we look at the I component forces, so we've got T2 cos 30, which is T2 root 3 on 2, equals T1 cos 45, which is T1 times 1 on root 2. J component, sine 30 a half T2, sine of 45, 1 on root 2. So that should be a T1 time on root 2 is equal to 8. So if we just manipulate the I component, we'll get T1 is equal to root 6 on 2 T2. Substitute that into the J equation. So I've got an equation purely in T2. In reality, for this example, the surds are messy. Obviously, you could multiply everything, just get a common denominator, multiply everything by 2 root 2, or multiply everything by 2 root 2 to end up with a root 2 on T2, 2 root 6, 16 root 2, group our terms together, and we end up with an 8 times root 3 minus 1. In reality, we'd have a CAS for this, especially this year for us, and we just solve that on our CAS. And then from equation 1, we know that T1 is equal to root 6 on 2 times T2. So if we multiply the root T2 value by root 6 on 2, I get an equivalent T1 expression. Okay, so in some ways, I think the hardest part of that problem is just manipulating all those surge expressions and those exact values and all that sort of thing, which is really good practice to do. But for us this year in this topic, I'm more interested in you sort of getting these two equations here, resolving our forces in a horizontal and vertical direction. All right. If we have an inclined plane, all right, what we do is we resolve, and I alluded to it earlier, we resolve perpendicular and parallel to the plane. Okay, so they're the directions that we take. All right, so if we consider the diagram that we've got here, We've got a body of mass, 10 kilogram weight acting vertically down. It's held at rest on a smooth plane by a 5 kilogram weight force acting up in a direction of some sort. So we're looking to find the angle of the weight force that would hold that particle in place. Okay, so typically if we've got a particle or a book or something on a table and we raise the table up, it'll slide down the plane. Okay, so if we've got a tension force or a force holding that particle in place so it doesn't fall down, we want to work out what angle we need to hold that force at. All right, so let's consider the diagram that we've got here and just work out the way in which we resolve it. So the directions we take are parallel to and perpendicular to the plane. Okay, because my normal reaction is always perpendicular to the plane. Okay, so that normal reaction is perpendicular to the plane. So what we want to do is then work out the component of the force that's acting parallel to the plane, the component of this weight force, which is here, that's acting down the plane. Okay, and we'll look at that in more detail, if not this year, next year. And those two forces must be equal. So if we concentrate on the I direction, let's think about this weight force, this red 10 kilogram weight force acting vertically down. What part of that weight force is acting down there, down the plane? Okay, so if we again consider this right angle triangle that we create with the red weight force, there's a little right angle there. So that angle's 90, that's 20, that's got to be a 70 in there, which means I'm now creating another triangle, okay, where this blue line, which is acting perpendicular to the plane, so that angle in there is going to be 90 degrees. So what we actually find is this angle in here is 20 degrees, and we probably won't talk about it a lot this year, but the component of my weight force that's acting down the plane will always be m sine theta or mg sine theta, depending upon which units we're going to use. So it's always going to be sine of the angle times the weight force acting down the plane. All right. So in this case, there's my opposite side, there's my angle. So it's 10 sine 20 degrees. So I've got acting down the plane is that 10 sine 20 degrees. Acting up the plane is just this component of the green force. That's the adjacent side, which is 5 cos theta, whatever the angle happens to be. Right? Now, they're the only horizontal forces or the forces acting parallel to the plane that are in place, so they have to equal to each other, which means that's enough information to find the angle. So if we just rearrange that, cos theta is equal to 10 sine 20 on 5, which is 2 sine 20, which turns out to be almost a 45 degree angle, a 46.84 degree angle. Okay, so it's that resolving of the forces. Again, there's nothing to say that we couldn't have solved both of those, again, using my triangulation of forces. Okay, but it is good practice to resolve our forces in different directions because it's something that becomes more significant as we go on. Last example, again, we have another plane, particle of mass 20 kilograms lies on a smooth plane inclined at an angle of 30 degrees to the horizontal. It's held at rest by a force acting parallel to the plane. Okay, so there's that black force acting parallel to the plane. Show the forces acting on the body. So we've sort of got that. We've got our reaction force or our normal force. I've got the weight force acting vertically down, and I've got my force acting up the plane. This weight force, we know that weight force has a component acting down the plane, and that component is given by 20 times sine 30. Okay, which in actual fact we work out over here. So the equations of motion for this situation, so the terminology is a bit different. It's really just saying find out, let's work out all the forces acting. So there's my I component. I've got the black force acting up. I've got the weight force, 20 sine 30 degrees acting down. if I wanted to do the J component, I've got a green normal force. Oh, where's my green gone? There it is. My green force acting up N, and that's equal to, well, this component of the force acting down, and that's the adjacent side, which is 20 times cos 30 kilogram weight. And if I wanted to find that normal force, cos of 30 is root 3 on 2, so it's 10 root 3 kilogram weight. So I've got a 10 kilogram weight acting down the plane, and I've got a 10 root 3 kilogram weight acting perpendicular to the plane. All right. So in actual fact, the force is acting. All right, so there's my resolving of forces process. Let's have a go.